Hello and welcome. In just 1 month, NASA will launch SPHEREx, a new space telescope that will map the universe like no telescope has before. I'm Raquel Villanueva, coming to you live from NASA's Jet Propulsion Laboratory in Southern California. SPHEREx will scan the sky in infrared and create an all-sky map. This will help us learn why the universe looks the way it does, how galaxies form and evolve, and where water and other key ingredients for life can be found in our galaxy. And in case you're wondering what SPHEREx stands for, and who knows, there may be a pop quiz later, here it is. Spectro-Photometer for the history of the universe, Epoch of Reionization, and ICE's Explorer. But for now, we'll just stick with SPHEREx. Today, members of the mission will talk about the Space Telescope's science goals and the final preparations taking place. Our panelists today are NASA Astrophysics Acting Director Shawn Domagal-Goldman, SPHEREx Project Manager Jim Fanson, Deputy Project Manager Beth Fabinsky, Principal Investigator Jamie Bach. And with NASA's Launch Services Program, we have Cesar Marin. He's the NASA SPHEREx Integration Engineer. For anyone who would like to submit a question, you can use the Ask NASA hashtag, and our phone lines are now open to the media. You can ask a question by pressing *1. And in just a moment, we are going to hear from our JPL Director, Laurie Leshin. But first, I would like to welcome Nikki Fox, Associate Administrator with NASA's Science Mission Directorate. Good morning, Nikki.
Good morning, Raquel. Thank you so much for including me today. It's always great to be able to talk about the excitement at NASA Science. But before I do want to take a moment to say that our hearts are really heavy this week for those who lost their lives in the tragic plane and helicopter crash at Ronald Reagan Airport on Wednesday night. Also, our continual condolences go out to those in California who've lost everything in the fires, including our incredible NASA and JPL families who work with us every day with our incredible teams to put more and more incredible science into space. The missions that we launch are groundbreaking and inspirational, and of course, SPHEREx is just a great example of one of those missions, and we're excited to be able to talk about SPHEREx today. NASA really leads the world in uncovering the secrets of the universe and searching for life beyond our home planet. We strive every day to push the boundaries of what is known of the cosmos and to share those new discoveries with the world. NASA science is bold and it's balanced, and our missions inspire and challenge both the nation and the world to make the seemingly impossible possible. SPHEREx is an ambitious mission, and we are literally mapping the entire celestial sky in 102 infrared colors for the first time in humanity's history. And we will do that every 6 months. This has not been done before on this level of color resolution for our all-sky maps. Everything in NASA science is interconnected, and our missions and our data build upon one another to expand our understanding of the universe and our place in it. We are looking to understand the origins of life across NASA's science portfolio in many, many different ways. SPHEREx will search for the ingredients of life right here in our universe using technologies adapted from our Earth satellites and our interplanetary spacecraft. Being this close to SPHEREx is making me really excited about all of our NASA flagship missions. The Nancy Grace Roman Space Telescope is on track for completion next year. And of course, the Habitable Worlds Observatory will be made in ways that we're just beginning to imagine. Across our NASA science portfolio, we're looking for the ingredients of life in our universe, and SPHEREx, and soon the Habitable Worlds will also be looking for those ingredients too. NASA is leading the world in a new era of survey astronomy. And so, from me, from all of us here at NASA Science, congratulations to the SPHEREx team. We cannot wait to see the incredible data that will be delivered back to us in the years to come. And now, my great pleasure to throw it to my good friend, Laurie Leshin.
Thank you so much, Nikki. It's great to have you on with us this morning. We're really thrilled to say the SPHEREx team at JPL and around the country have been working hard to get SPHEREx ready for launch. And of course, that has been especially challenging in these last few weeks as we have been grappling with the impacts of the devastating fires which took place really right next to JPL. And I think as many out there know, more than 200 JPLers lost their homes, and people on the SPHEREx team have been impacted. And I just want to give a huge shout out, first of all, to everyone who's been impacted by the fires, to see the community, even beyond JPL, our whole Southern California community rally in support of people who have lost everything in the fires has been heartwarming. It's a heartbreaking situation, but it's been heartwarming to see how people have come together in support of one another. And trying to get our SPHEREx beautiful spacecraft, which you'll see in a moment, transported from where the final integration took place in Colorado to the launch site in California itself was a real challenge because of the impacts of the fires. So again, just a huge shout out to our SPHEREx team across the country who has helped us get to this point of being ready to launch. I am really excited about the cosmic mysteries that SPHEREx is going to reveal with its all-sky survey. You're going to hear a lot more about that from our incredible panel here today. What I would like to do is give a shout out to it's really not just a national team, it's an international team, as all of our missions happen because of teamwork. I'd like to acknowledge first our partners on campus at Caltech. As many of you know, we at JPL are Caltech employees, but this mission especially has a PI from Caltech, so that's a special partnership between the Caltech campus and JPL at the laboratory. To BAE Systems in Colorado, who's our industry partner. Everything we do is in collaboration with the commercial sector here at JPL, and BAE has done an amazing job building this integrated telescope and spacecraft system. The Korea Astronomy and Space Science Institute, who contributed test equipment and science payloads, and of course our NASA colleagues, both NASA headquarters and our dear friends at the Launch Services Program have just been amazing to work with throughout the SPHEREx program. I'm just so proud of this extraordinary team. We say dare mighty things together here at JPL. This team embodies that. And we're also excited to have a couple more launches coming up in the next few months, so you'll be seeing more from us, Lunar Trailblazer, as well as NISAR. So lots going on here at JPL. And Raquel, I'll hand it back to you to get into the panel.
Great. Thank you so much, Laurie. Now I will hand it over to Shawn.
Thanks, Raquel. I am so excited to be here close to the launch of SPHEREx, which I am really excited about. I'm going to tell you more about that in a minute. But first, I want to echo Laurie's thanks to all our partners involved in making this mission a reality. I'm especially grateful to Laurie, your team, and also the other teams in California who have faced just tremendous challenges the last few weeks, but have demonstrated tremendous resolve to get us to this point. And as Nikki said, those partnerships are important because NASA's leading the world in uncovering the secrets of the universe, searching for life beyond Earth. Those are challenging things, and we overcome challenges by bringing together the best the US space community has to offer and combining that with our international partnerships so that we can lead the world in making those new discoveries. Now, the discoveries that SPHEREx are going to make, it's going to answer a fundamental question. How did we get here? And it's going to answer that question in a number of ways. First, it's going to study a huge number of galaxies at various points in their histories to understand their origins and evolution. And in fact, it's going to study so many, we're going to be able to go further back in time than the galaxies themselves, because we're going to be able to sort of take a snapshot at that point in the universe's history and have so much data on that point that we'll be able to go backwards in time, closer to the origins of the universe itself. And later in cosmic time, we're also going to, because we're surveying the sky, look at the places between stars to see where ices and organics make their way from that space between stars to stellar and planetary systems and ultimately to the planets. Shout out to our team in SPHEREx in the Planetary Division, because they pick up that story and then tell how it traversed in our solar system to planets like our home one. Now, SPHEREx is going to do all of that science by, conducting an infrared spectroscopic survey of the full sky. This will both complement and add to the fleet of missions observing the sky across different types of light and different capabilities and observing techniques. No single instrument, no one instrument, no single mission can tell us the full story of the cosmos. Those answers, to the big questions like that, they come from the power of combined observations from combined observatories. Can we bring up the first image I've got? As you'll see, NASA has more than 20 astrophysics right now, either operating or in development, on top of our programs for smaller satellites and suborbital missions. Now, each one of those are like our own kid. Like we love them all, and we love them in different ways because they each have their own kind of special skill set that adds to that fleet. Now, some of those missions, like NASA's James Webb Space Telescope, they're point and shoot observatories. You have to think about like taking a picture of another person with your smartphone, right? Those look deep into the universe to study specific targets in great detail, but they often have a narrower field of view, just like taking a picture of a single person. But if you want to get the full picture, we need survey missions like SPHEREx, also like the upcoming Nancy Grace Roman Space Telescope, to quickly study broad swaths of the sky and give us data on billions of objects. If taking a snapshot with JWST is like taking a picture of a person, what SPHEREx and other survey missions do is almost like going into panorama mode when you want to catch a big group of people and the things standing behind or around them. Now, once we do that, as scientists, we get to search that huge data trove for trends or follow up on a more detailed view with those targeted telescopes. The point and shoot ones might go and look at something interesting in more detail. And we can get the second image. This will show you how we also look at different wavelengths of light. In the case of SPHEREx, we're looking at infrared light, wavelengths longer than our human eyes can see. Now, we have other observatories that look in those wavelengths that you're looking at now. What makes SPHEREx unique is it's a high precision spectroscopic map of the sky in those infrared wavelengths. Now, the survey, you're going to hear more about that in a bit. It's going to contribute unique pieces to the cosmic puzzle of how the universe got to be the way it is today. Now, that survey is also going to produce that data set I mentioned, and that has its own power. It's going to create the ability for people to access the data for their own research and discoveries. And it's going to broaden the access to discovery, allowing the best research to happen based on the qualities of the ideas that people bring forward. Now, if it sounds like a challenge to squeeze all of what I just said into a single mission, I assure you it has been one. Now, we're able to overcome those challenges because we've got great teams figuring these things out every day. In particular, I want to give a shout out to the SPHEREx team, and I'm going to hand it over to Jim Fanson, the project manager for SPHEREx at NASA JPL. Jim?
Thank you, Shawn. We are headed to the launch pad, and we're ready to put SPHEREx into orbit. If I can have the first video clip, please. The SPHEREx spacecraft has just completed standalone integration activities at the launch site, and after being transported across the country from BAE Systems in Boulder, Colorado to the Vandenberg Space Force Base in California, the vehicle was unpacked from its shipping container and inspected, and a series of performance tests were then conducted, exercising all the various subsystems of the spacecraft and the science telescope. We're about to begin the combined integration activities where we will physically mate SPHEREx to the launch vehicle adapter, which is located above the secondary payload called Punch, forming the payload stack. SpaceX will then encapsulate the payload stack inside the launch vehicle's protective fairing. This encapsulated assembly will then be transported across the Space Force Base to the SpaceX launch pad, where it is attached to the Falcon 9 rocket. And we'll hear more about the launch vehicle from Caesar in a few minutes. We know the spacecraft is ready for launch by final testing of the vehicle itself at the launch site, which is now completed, and by the certification of flight readiness process that assures that all necessary testing, analyses, operations tools, and training of the operations team have been completed according to JPL and NASA requirements. A series of technical reviews have been convened to establish this readiness. If I can have the second video clip now. Over the past couple of years, extensive testing has been performed at JPL, Caltech, and at BAE Systems. The spacecraft has been exposed to the harsh environments it will experience during launch, including intense acoustic noise and vibration, and the hot and cold environments it will feel in the vacuum of space. Every subsystem of the vehicle has been tested as closely as possible to how the spacecraft will operate in space. Since arriving at the launch site earlier this month, Integration and testing has proceeded smoothly and on schedule by a skilled team from Caltech, JPL, BAE Systems, Astrotech Space Operations, and the NASA Launch Services Program. Looking forward to launch day, most of the team will be located on console in the Mission Director Center at the Vandenberg Space Force Base or at the Earth Orbiting Mission Operations Center here at JPL. Some of the team will be at the Payload Processing Facility at the launch site and some at the SpaceX Launch and Landing Control. If I can have the final image, please. For me personally, the most exciting thing about SPHEREx is the ability to make new measurements of the cosmos that will inform our understanding of how the universe we see today came to be, and possibly also to advance our understanding of fundamental physics itself. We're very privileged in the long story of the human existence on this planet to live at a time where we can actually answer questions about the universe. So it's very satisfying to work on a mission like SPHEREx. With SPHEREx now ready to begin its journey into space, my deputy, Beth Fabinsky, will explain more about how the mission is designed and how SPHEREx will make its measurements.
Thank you,
Beth?
Jim. SPHEREx is a testament to doing big science with a small telescope. Like all space telescopes, there are two parts to it, the payload and the host spacecraft. Can we bring up the side-by-side images of the spacecraft? The payload includes our instrument, as well as supporting hardware to attach it to the spacecraft and protect it from the launch and space environments. The instrument is not just the telescope optics, but also detectors that capture infrared light and transform it into electric signals. In addition, there are electronics that process those signals and send them on to the spacecraft for transmission to the ground. Like most NASA missions, there is something unique and novel about our mission, and in this case, it's our unusual instrument design. We have one telescope that sends light to two focal plane assemblies, where a scene from the sky is focused and captured. Can we bring up the image of the focal plane assembly? These focal planes each consist of a set of 3 detectors sandwiched together with special filters made of coated sapphire, so that the wavelength of light captured by the detectors varies along the length of each detector. So along the length of each exposure we take, we're sensing a slightly different wavelength of light. Think of it as if our instrument is looking at the universe through a set of rainbow-colored glasses. Now, the most noticeable thing about our space telescope is not the instrument, but the supporting payload hardware that protects it and surrounds it. Let's do a side-by-side with the photon shields and the V-groove radiator, please. We have 3 concentric cone-shaped photon shields. They protect the instrument enclosed in the center from sunlight and earthshine, together with 3 curved plates at the bottom of the payload, called a V-groove radiator. They help radiate heat away from the warm spacecraft beneath the payload. This is important because our detectors need to be minus 360 Fahrenheit. That's because they're infrared detectors, and if they are too warm, they will be blinded by their own warm glow. We also protect our instrument from the heat and brightness of sunlight and earthshine by not pointing the telescope too closely toward the sun and earth. We can do this and still point at many places, in fact, all places on the sky, because we have a very special orbit called a dawn-dusk sun-synchronous orbit. That means our orbit plane, or the circle inscribed in space by our orbit, is always facing the sun as the Earth revolves around the sun. The telescope can point out and away from the Earth and at the same time point normal to the sun line. And it can prevent us from getting sun and Earth on our cold, dark detectors. Our spacecraft was developed and tested by BAE Systems. It weighs about 1,100 pounds, so a little less than a grand piano, and uses about 270 to 300 watts of power, less than a refrigerator. It produces more power than it needs, using a fixed solar array very much like one you might have on the roof of your house. What's exciting to me about this mission is that it's an all-sky survey. While there are telescopes that can see celestial objects in great detail, like a Hubble or a James Webb,
They can only see so much of their sky because of their limited field of view. Our telescope has a very large field of view, about 11 by 3.5 degrees, and we see the entire sky twice each year. So if Hamlet is right, and there are more things in heaven and earth than are dreamt of in our philosophies, SPHEREx may capture that in its all-sky spectral survey. And with more on that, I'd like to hand over to Jamie Bach, our principal investigator.
Thank you, Beth. I'd like to say a few words about SPHEREx's science. Even though SPHEREx uses a small telescope, it looks at the universe in a new way, mapping the entire sky in infrared spectroscopy. So this new capability allows us to address some of the most compelling questions in astronomy. How did the universe begin? How did galaxies form and evolve over cosmic history? And what's the origin of water and organic materials in our galaxy? So let's take that first question. How did the universe begin? Well, we can ask ourselves, why does the universe look the way it does today? The universe we see today is very smooth on the largest scales, and it also has a flat geometry. The modern explanation for these phenomena is a theory called inflation. Inflation says that in the first moments of the universe, literally a trillionth of a billionth of a second after the Big Bang, the observable universe went through a remarkable expansion, expanding a trillion fold. And that expansion expanded tiny fluctuations smaller than an atom to enormous cosmological scales that we see today traced out by galaxies and clusters of galaxies. Even though inflation was invented in the 1980s, it's been tested over the intervening decades and has been consistent with the data. So while we have this general picture, we still don't know what drove inflation or why it happened. So what SPHEREx will do, will test certain models of inflation by tracing out in 3 dimensions hundreds of millions of galaxies over the entire sky, and those galaxies trace out the initial fluctuations set up by inflation. So now let's go to our second question. How do galaxies form and evolve over cosmic history? From studying many galaxies, astronomers have a general picture that the first stars and galaxies turned on a few 100 million years after the Big Bang in an epoch known as cosmic dawn. Again, from studying many galaxies, astronomers see that star formation peaked about 5 billion years after the Big Bang, and it's been on a slow decline over the last 10 billion years or so of cosmic history to today. And this picture's been built up by studying galaxies individually, but it might not be a complete accounting. SPHEREx, with its small telescope, is going to address this subject in a novel way. So instead of really counting very deeply individual galaxies, SPHEREx is going to look at the total glow produced by all galaxies. This cosmological glow captures all light emitted over cosmic history from galaxies and, well, anything else that emits light. So it's a very different way of looking at the universe, and in particular, that first stage of star and galaxy formation must also be in this cosmic glow. And by looking this way, we can compare to counts that have been built up with large telescopes and see if we've missed any sources of light. And now let's go to our third question. Where is the water in our galaxy? So as astronomers, we know that our galaxy, and all galaxies, contain enormous reserves of water and organic materials in the interstellar clouds where stars are born. Now, interestingly, that water isn't in the form, by and large, of liquid or vapor. It's actually in the form of ices, ices on the mantles of interstellar dust grains. And it's not just water. There are organic materials in those ices as well. This is a topic of some interest for us on Earth because the water we see here on Earth's oceans, astronomers believe that initially came from these interstellar reservoirs of ices. So this picture's been built up by studying of order 100 or so cases of these measurements in the infrared to see the abundance of these materials. And what SPHEREx is going to do with its enormous survey capabilities is study the abundance of water and organic ices over millions of lines of sight over the entire sky. And that will trace out the abundance of water ice from the initial interstellar clouds through the stages when stars are just starting to turn on. So key to all these investigations is infrared spectroscopy. We split the light into multiple colors, and in splitting up the light, we can use that to determine the distance to galaxies to build up that three-dimensional map. And we also see the fingerprints of water and other interstellar ices. This is a new capability, and with any new capability comes the potential for discoveries and surprises. And we want to maximize that discovery potential. So we put out our data rapidly to the community in calibrated form within 2 months from when the data is taken. The astronomy community can then go through the data. In fact, anybody can. It's publicly available. And study their own interests, science interests. And of course, our team will be working on the same data on those three compelling science themes that I mentioned. We build up this spectral survey by taking 102 pictures at every point on the sky. And in 6 months, we cover the full sky. That gives us a complete survey and a spectrum for every point on the sky. Over our 2-year baseline mission, we get 4 such surveys, and that's our SPHEREx data set. So for me, obviously I'm very excited about SPHEREx's science, but I have to say that the moment I'm looking forward to is once we've popped the lid off the telescope and taken our first image that'll tell us everything's working as expected. So with that, I'm going to turn it over to Cesar Marin, who's going to tell you about launch services.
Thank you, Jamie. Yeah, the Launch Services Program is super excited to provide a ride to space using a single rocket, not only to the SPHEREx satellite, but also to the Punch satellite, thus enabling scientists to get a better understanding of the universe and the sun. NASA Launch Services Program, otherwise known as LSP, matches the satellite's needs to the appropriate commercial rocket. In this case, while securing a SpaceX Falcon 9 rocket to SPHEREx, we're taking advantage of the extra capacity for a second satellite going to a similar orbit. NASA Heliophysics Punch will be the ride share on the February 27th launch. LSP functions as a broker, matching the satellite with the best suited rockets, managing the launch process, providing support from pre-mission planning to post-launch. Now, please bring a picture of the Falcon 9 launch. SPHEREx and Punch will be launching from Space Launch Complex 4E at Vandenberg Space Force Base in Central California. The beginning of the riveting 30-second launch window will be at 7:09 Pacific Standard Time on February 27th. The amazing SpaceX Falcon 9 full thrust rocket has more than 400 successful launches. Please show the picture of the booster return. This is the third launch of this reusable booster, which was previously flown on the Transporter 12 mission on January 14th, similar to what you see here on the photo. After launch, the booster will be applying its phenomenal capacity of returning once again to the landing zone 4 at Vandenberg Space Force Base about 8 minutes after launch. Weather permitting, the launch will be visible from the California coast. This will be the Launch Services Program 106th full end-to-end mission and the 11th primary mission to fly with SpaceX. While SpaceX uses this particular launch pad for various customers, the last NASA launch from this location was the SWAT mission back in December of 2022. Now I will be switching to what is happening with the satellites. Please show the picture of SPHEREx arriving at Astrotech. SPHEREx arrived by truck at Astrotech Space Operations at Vandenberg Space Force Base on January 14th. Like Beth mentioned earlier, SPHEREx will be deploying to a sun-synchronous orbit, circling the Earth pole to pole instead of around the equator. Please show the picture of the Punch satellites. Punch is made up of a constellation of 4 satellites, which arrived by truck at Astrotech on January 18th. Punch is going to a similar sun-synchronous orbit and will deploy during 2 separate events, just a few minutes after SPHEREx deploys. Now I would like to cover the process for the satellites arriving at the launch pad. The excited integration of the 5 satellites with the rocket hardware will begin in mid-February, starting with mate to the rideshare dispenser, payload fitting, and payload adapter. The integration of the 4-punch satellites will be performed first. Then the SPHEREx satellite will be integrated on top of the stack. SpaceX will encapsulate the satellites into the payload fairing at Astrotech before transporting the entire assembly to Space Launch Complex 4 East, where it will be mated to the rocket in a horizontal position. The rocket would then roll to the pad and then finally go vertical. Please show a picture of the SPHEREx satellite. What makes this launch special for me? My contributions with supporting the mission design and mating the satellites to the rocket is that launching this mission is going to help scientists understand the universe and the sun better. This is also my first SpaceX mission. All my other previous experience has been with other type of rockets. Now back to you, Raquel.
Thank you so much, Cesar. We are now ready to take media questions. Remember to press *1 to get put in the queue, and please direct your questions to one of the panelists. We're also taking questions through the hashtag AskNASA. Now, our first caller is Marcia Dunn from the Associated Press.
Yes, hi, hoping you can hear me. Couple quick questions. I'm looking for a mission cost, a total mission cost, if you don't mind. 102 colors in the infrared. Up until now, what's the most colors you've been able to gather on a single mission? And lastly, how far back in time do you think you will be able to go with this survey? Thank you.
All right, thank you, Marcia. We'll start the first half of your question with Shawn.
So for the budget, the total life cycle cost, including launch and operations for SPHEREx, under our current planning is $488 million, and that includes the things that are yet to come.
Great, thank you, Shawn. And for the second half of your question, I will toss it over to Jamie.
Right, so the question about the number of colors. There are many capable spectrometers that are in space. JWST has some of the best ones. So really the thing that makes SPHEREx unique is mapping the whole sky like that. In terms of all sky survey missions, generally these have been done in photometry, looking at the sky in broad bands, and handfuls of broad bands, not this complete spectrum. So I hope that answers that question.
Thank you, Jamie.
And how far back in time can you go?
Oh, right, how far back in time? Well, so as I said, what we're doing is we're observing galaxies past, half the universe's age. But those structures were set up initially in the first moments by inflation on very large cosmological scales. Those came from the Big Bang itself. So we're using the distribution of these more recent galaxies to understand a phenomena that happened in the very early universe.
Great, thank you, Jamie. And up next, we have David Dickinson with Sky and Telescope magazine.
Thank you. This question is probably for Jamie Bach. I was curious about the timeline for the window for getting science results from the mission, like after launch, and if there's any kind of window, if the mission doesn't go on February 27th, that we'll see the mission go later. Thank you.
So if you're referring to the data releases, the main form of data release is that we put out what we call calibrated spectral images, and those come within 2 months of observation. So obviously we have to get into space, we have to do our in-orbit checkout, but once the survey starts, we need about 2 months to process that data in a calibrated form, and so that'll just shift according to whenever our launch date is, if it were delayed. We do recalibrate after we've completed a couple of surveys, and we put out some additional data products, including the core data products that come out 3 years after launch.
Great. And up next, we have Josh Dinner from space.com.
Hi, thanks so much. I wanted to ask if there were any engineering constraints with the spacecraft itself that have limited the type or amount of data you'll be collecting. And once the mission reaches its 2-year endpoint, is there any potential for a prolonged operation?
Beth, do you want to start with that one?
I'll take that one.
As far as, I wouldn't say there are any constraints that limit the data that we're collecting. We're getting the right amount of data we need to do the science that Jamie has been describing. So I would say that's the fair answer to that question. And the second part of the question?
Anything that limits the lifetime.
Okay. Well, we don't have onboard consumables like propulsion system with fuel in it. So we don't have that. There are other kinds of consumables on a spacecraft, like switch cycles and memory rights. We do have those, but they're not a significant limitation to the lifetime of the spacecraft. And yes, potentially the mission could be extended and could go longer than the 2 years if NASA decides to do that.
We also don't have stored coolants, so that structure you see is to radiate the heat out to space, yes. And so we are not limited by coolants either.
That's right.
Thank you.
Thank you. And up next we have Jeff Faust from Space News.
Good morning. Quick question for Caesar. I may have had a quick audio dropout. If you could give the projected date and time of the launch. Thanks.
Yes, thanks for the question. It will be February 27th, and the time is 7:09 Pacific Standard Time.
Great, thank you. And we're actually getting some social media questions in. So this first one I think will be for Beth. Matthew Henson on YouTube asks, what are the set of cones made out of? Will the protective shields be against the light of the sun and the earth?
Yes, the shields protect us against sunlight and earthshine, and they are made out of aluminum honeycomb.
Thanks. And up next we have TikTok on X wants to know, how does the SPHEREx use infrared wavelengths to contribute to its scientific objectives, especially in comparison to visible light observatories? Jamie?
Okay, yeah, we look in the infrared. You can think of, there's a couple reasons. So one reason is that starlight, as we look back in time, it redshifts to longer wavelengths and goes into the infrared spectrum. Another important thing is that dust in our galaxy obscures starlight in the optical, and that obscuration gets reduced into the infrared. So especially as we build these all-sky maps of galaxies, we have to take into account that kind of behavior, and it's more favorable to do that in the infrared. And finally, these signatures of water ices and interstellar ices show up in the infrared, and really those are at wavelengths that are really difficult to do from a terrestrial observatory.
Thank you, Jamie. And this one's for you, Jim. It's from AstroPeep05 on Instagram, who wants to know, how many people work on a project this size?
A good question. So we have in our development a profile for the workforce, and it changes a bit depending on what phase we're in. At the peak, I think we were about at 150 full-time equivalents. Not everybody works full-time, of course. And we're considerably a smaller team now. We've kind of necked down to a single workflow with the vehicle being processed and getting the ground system ready for flight. So for a small mission like this, it peaks out at about 150.
Great, thank you, Jim. Up next, we have a question for Caesar. Why is it being launched together with another mission?
Very good question. So the reason for that is we're going to a very similar orbit. So it just turns out that the primary spacecraft already identified the location where they wanted to be dropped off in space. And it just turns out there was another satellite that was being developed that happens to be needing a ride to a very similar location in space. So LSP used that capability from the rocket. It has excess capability, so we were able to actually fit in a second satellite, which actually is a constellation of 4 satellites actually. So we were able to include it in the ride, and it's just a coincidence that these 2 satellites happen to be ready about the same time and also going to the same general area in space. So that was just a bunch of coincidences happening at the same time, so we took advantage of that to save the government a lot of money by providing a ride to 2 satellites at the same time.
Great, thank you so much, Caesar. And just a reminder, if you want to get put in the media queue for questions, press *1. And we are going back to Marcia Dunn with a follow-up question.
Yes, hello again. What is the targeted orbit? How many miles, kilometers up will not only the SPHEREx be, but also the Punch satellites? And why Vandenberg? Does it just give a better lift to polar orbit than the Cape, although SpaceX has been launching polar flights out of here lately too?
Who wants that one?
Well, I can say for SPHEREx, our altitude is 650 kilometers, so that's considered low Earth orbit. And for Punch, I guess I would hand it over to Caesar.
Yeah, what I will say to that is typically for missions that are going on a polar orbit, Vandenberg is typically the primary location for that. And it's correct, SpaceX does have the capability because they have a very, very powerful rocket to be able to go to polar orbits, also from the Cape. But yeah, ideally you want to launch from Vandenberg for those missions because it's essentially cheaper, it's more efficient to launch from here, from Vandenberg, for polar specific orbits.
And what orbit for the Punch satellites, please?
It's a similar orbit. They're going to be essentially separated only about 11 minutes apart. So the orbit is very, very similar. It's in the same general area.
Thank you.
Great, thank you. And we are also going to return to a previous question, hand to Nikki Fox, about why the two missions are launching together.
Oh yeah, thank you so much. Yeah, that is a program, sort of an initiative we've had here in the Science Mission Directorate to actually look at getting more science into space for less cost. And so when we have missions that are looking like they're going to go to the same place, it's not always easy. I don't want to make it sound like it's a simple thing, but when we can take advantage of that, then we work very hard to actually align those schedules. So it was a very, very deliberate thing. It wasn't actually a coincidence. We actually, when we selected Punch, and actually Tracers is another heliophysics mission that will launch later this year. They were all going to a very similar place as SPHEREx. And so we actually deliberately worked very closely, the Heliophysics Division with the Astrophysics Division, to be able to do that ride share so that Punch gets a ride to space instead of us having to procure two launch vehicles. So it's really just a more efficient and effective way of getting more science into space.
Thank you, Nikki. I understand that Marcia has another question as well. All right, while we work to fix that, I'm actually going to take a social media question. Rachel of the Sea on Instagram wants to know, as an astrophotographer, I'm wondering, will the process data be publicly available? Jamie?
So as I said, the initial release within 2 months is in this form of spectral images. So those are like the rainbow colored glasses. Each picture will look like those glasses, basically. And to get information, you need to compose multiple images from our spectral image library. Now there will be tools to do things. So for your sorts of interests, there will be a 3D sky viewer, which allows you to look at pieces of sky, all the colors in a data cube. But there are other tools for astronomers to take the photometry of their favorite object and all the colors and all the observations that we have.
Thank you, Jamie. And Beth, thank you so much for bringing those sunglasses. They're really coming in handy as a great prop. AC on YouTube wants to know, why does an infrared telescope when there is already James Webb? So let me just rephrase that. Why is there an infrared telescope when we have James Webb? Shawn, we can start with Shawn, and then Jamie, if you want to weigh in.
Yeah. For me, it's the complementarity of the difference between taking that picture of a single person, focusing in on it in great detail, which is what the James Webb Space Telescope will do, versus panning across the entire sky, which is what SPHEREx is going to give us. And SPHEREx might find some stuff when it looks at the whole sky that astronomers are like, hey, what's going on over there? I want to study that in great detail and then follow up with JWST. Jamie, I don't know if you want to build on that on your end.
No, I think that's basically right. I mean, JWST is incredibly capable, but it's a big telescope and it's hard to move to cover the entire sky. For example, with our survey of ice regions over millions of sources, you can sift through those objects and pick the most interesting ones, and they could be followed up with JWST or another NASA capability.
Thank you, Jamie. I have another question from you for M. Sadra 1010 on Instagram wants to know, how many years will it take to complete the map?
Right, so the first survey, we survey the sky rapidly. And so as we're going around the sunrise-sunset line of the Earth, we're surveying basically a strip, as that video showed. And then as the Earth goes around the sun, the plane of the orbit follows the sunrise-sunset line. So actually you close the circle within just 6 months. So 6 months we get a complete all-sky survey in all the colors, and then we do that 4 times during our 2-year baseline mission to give four surveys. And those additional surveys allow to check for data consistency. They allow us to see events that might change and make the data set just that much richer.
Thank you. We have some more social questions coming in, so keep them coming. We have the Dave Stewart on Instagram wants to know, how long did it take to manufacture? I don't know if we want to do Jim or Laurie on that one.
Well, I guess what I would say is the mission was originally selected in 2018 during the first Trump administration, actually, and so it's exciting to see it launching now. And so we've been working on it since then, but to actually build it, let's turn it over to the mission folks to tell us.
Yeah, so typically the first couple of years of the mission is in the design phase, and the manufacturing then starts after what in NASA we call a critical design review. So I would say that the manufacturing process for SPHEREx has been going on for about the last 4 or 5 years, depending on how granular you want to consider the start of fabrication.
Yeah, because you build some of the payload elements quite early on, and you do engineering models that you manufacture, so it can go back quite far in the development of the mission.
Yeah, some of the items are long lead, meaning it takes a long time to manufacture them, so you want to get an early start. And in those cases, you can even start fabrication prior to this critical design review.
Great, thank you all for that answer. And Laurie, I actually have a question for you. It's from Coconuts. 0824 on YouTube wants to know, what's the most impactful data JPL is looking for with this mission?
Oh, that's a question for me. Well, I mean, I think Jamie has done an outstanding job of sharing the science. And the exciting thing about this mission to me, and not being an expert in all of the areas, but it's a small mission with a big impact, right? And whether that's looking at ices in forming solar systems elsewhere across the galaxy, or understanding how inflation really formed the universe to look the way it did today, both those are pretty impactful things. And I love the variety of scientific results we're likely to get from this survey mission. And to do it all for under $500 million, sort of big science in a small package is one of the most exciting things about SPHEREx to me.
Jim, would you like to also take that question?
About the impact of the mission?
Of the data, or Jamie?
I think I'd defer to Jamie on that.
Thanks, Jim. Well, yes. I mean, I think that the 3 themes are what we built SPHEREx to do, and obviously we're really excited about that. But I would say, with a new capability like this, is always the potential for discovery and surprises. And we've polled the astronomical community, and they thought of some stuff as we were developing the mission that we hadn't thought of. And I sure would hope that we're going to have some of those, and they're probably going to come from the community.
One thing I would add is that I've been involved in several telescope projects, both in space and on the ground. And when we put a vehicle in space to look at the universe in a new way, it seems inevitable that you find things you had never expected to see. And some of the most exciting results are the things that you discover that really were unexpected. And I expect the unexpected to come out of the data for this mission as well.
That's a great way to phrase it. Expect the unexpected. And One of my favorite questions that came in was from Levi, who is 9 years old, from San Diego, and he has parental permission to ask, how far can it see into the universe, Jamie?
Yeah, so as I said, it depends what you mean by see. As individual objects, we have a small telescope, right? So we're not going to see galaxies forming at the dawn of time like JWST can. But we can do things that are unique. And so, for example, like I mentioned, this cosmic glow, that will contain light from those first objects. And if we can pull it apart, we can say something about how that process happened in aggregate. And these fingerprints from the Big Bang itself, we won't see the Big Bang, but we'll see the aftermath from it and learn about the beginning of the universe that way.
Great, thank you, Jamie. And that is all the time we have for questions today. So to learn more about the mission, visit nasa.gov/SPHEREx. And we also have everything you need to know in a press kit. You'll find that at go.nasa.gov/SPHEREx press kit. And be sure to follow the mission on social media at NASA JPL, at NASA Universe, and at NASA. I'd like to thank our wonderful panelists and their beautiful sunglasses in rainbow colors, as well as NASA's Nikki Fox and JPL's Laurie Leshin. Thank you so much.